Start with one request. Explain why the sky looks blue in exactly 2 sentences. A language model generates 2 answers, 1 token at a time. A person chooses which answer they prefer. Do this for many prompts and many pairs. These choices train a reward model to score completed answers. For this answer, the reward model gives a score of 1.2. That score belongs to the completed answer, not to any individual token. So how can that one score tell the model which parameters to change? To see what the final score can change, look at how the response is generated. The prompt and the tokens generated so far form the current prefix. From that prefix, the model assigns a probability to every possible next token. These probabilities add up to 1. One token is selected and added to the prefix. The model then calculates a new set of next token probabilities. In the diagram, branch width represents probability. Now follow 4 tokens: sunlight, scatters, in, air. The probability of this complete sequence is the product of 4 probabilities, 1 for each selected token. The model that produces these probabilities is called the policy or actor. Before using 1.2 to change the policy, we need to know exactly what that number means. For these 2 answers, the reward model gives A a score of 1.2 and B a score of 0.2. Preference training depends on the difference between those scores. 1.0? That difference corresponds to about a 73% predicted probability that A would be preferred over B. Now add 100 to both scores. They become 101.2 and 100.2. But their difference is still 1, so the predicted probability is still 73%. This shows that 1.2 has no fixed meaning by itself. The reward model learns relative scores from preference comparisons, not an absolute measure of answer quality. The reward score tells us which responses to favor, but not how far their probabilities should move. If the score is wrong, a large change can make the model worse. To make large changes costly, keep a frozen copy of the supervised model. Call it the reference policy. For any response, use the reward minus beta times the log of the probability of the response under the actor divided by the probability of the response under the reference. Across responses, this penalizes moving the actor away from the reference. Now consider 2 possible answers. The reference assigns 20% to A and 80% to B. Let A's reward be 1, B's reward be 0, and beta be 0.5. The resulting target reweights each reference probability by E raised to its reward divided by beta. A's weight is 0.2 times E raised to 1 divided by 0.5, or 0.2 E squared. B's weight is 0.8 times E raised to 0 divided by 0.5, or 0.8. Normalize those 2 weights. The new distribution assigns 64.9% to A and 35.1% to B. Reward favors A, but the reference probabilities still affect the result. A real model has far too many possible responses to calculate every weight. PPO therefore estimates the update using sampled responses. From that sampled batch, follow one response: sunlight, scatters, in, air. The actor that generated this batch is held fixed and labeled pi_old. At each position, use the same prefix and record the selected token's log probability under pi_old and under the fixed reference. Subtract the reference value from the pi_old value. This gives 4 log probability differences. A complete response probability is the product of its next token probabilities, so its log probability is their sum. Therefore, the complete response log ratio is the sum of these 4 differences. Here, they add to 0.5. Set beta to 0.05. Multiply each difference by negative 0.05, then add the reward model's 1.2 only at the final token. This gives 4 immediate shaped rewards. Their sum is 1.175. exactly the sequence level value, 1.2 minus 0.05 times 0.5. We now have one reward at each token position, but we still do not know how much each token probability should change. A separate model, called the Critic, sees the prompt and the tokens generated so far at each position. It predicts the shaped return expected from that prefix onward. For the 4 non-terminal prefixes, its predictions are 0.2, 0.1, 0.4, and 0.8. After the response is complete, the terminal value is 0. Start at the final token. Its shaped reward is 1.19. The next value is 0, and the Critic predicted 0.8. So the one-step prediction error is 0.39. Compute the same error at each earlier position. Set gamma to 1 and lambda to 0.95. Starting at the end, each advantage equals its one-step error plus 0.95 times the advantage at the next position. At the first position, the one-step error is negative 0.110. But after the later errors are included, the full advantage becomes positive 0.866. This backward calculation is called Generalized Advantage Estimation, or GAE. This does not say that the word sunlight caused the final score. It says that the sampled continuation from that prefix was better than the Critic predicted. In the policy objective, a positive advantage pushes the sampled token's probability up. A negative advantage pushes it down. Before any update, the actor generates this batch. At that moment, label the actor pi_old and store the probability it assigned to every sampled token. While training on this batch, those old probabilities remain fixed. An optimizer step changes the live actor pi_theta. Now evaluate the same sampled token from the same prefix under the updated actor. The token was sampled from pi_old, but its probability under pi_theta may now be different. To measure that change, divide the current probability by the stored old probability. This is the old policy ratio, rho sub t. Suppose the old probability was 0.3. If the current probability is also 0.3, the ratio is 1, no change. If it becomes 0.33, the ratio is 1.1, 10% higher. If it becomes 0.24, the ratio is 0.8, 20% lower. This ratio compares the updated actor with the policy that generated this batch. It does not compare the actor with the fixed reference policy. Take one sampled token with advantage plus 3. Its raw objective contribution is rho times 3, where rho is its current probability divided by its stored old probability. PPO compares this with the same product after rho is clipped between 0.8 and 1.2 and uses the smaller value. As this token becomes more likely, rho increases. At 1.35, the raw contribution is 4.05. The clipped contribution is 3.6. The smaller value is 3.6, so once rho reaches 1.2, any further favorable increase adds no benefit for this sample. If rho instead falls to 0.75, the raw contribution is 2.25, while the clipped candidate is 2.4. The minimum keeps 2.25, so this harmful decrease remains fully counted. Now, set the advantage to -2. In this case, lowering the sampled token's probability is favorable. At rho equal to 0.7, the raw contribution is -1.4. while the clipped contribution is -1.6. The minimum selects -1.6. Below 0.8, a further favorable decrease adds no benefit. If rho rises to 1.3, the raw contribution is -2.6, while the clipped candidate is -2.4. The minimum keeps -2.6, so the harmful increase remains fully counted. Clipping creates a plateau only after favorable movement, above 1.2 for positive advantage and below 0.8 for negative advantage. It changes the objective. It does not force every ratio to remain inside that range. Two policy comparisons now appear in the same PPO update. Both use the same sample token from the same prefix, but they have different denominators and different roles. During optimization of the current batch, compare the live actor, pi theta, with the stored rollout policy, pi old. Their ratio measures how much this token's probability has changed since the batch was collected. This is the ratio used in the Clipped PPO Objective. When the batch is collected, also compare the rollout policy with the fixed reference policy. Subtract the reference log probability from the rollout log probability, then multiply by negative beta. This produces the per token reference term used in the shaped rewards. When a new batch is collected, the current actor becomes the new pi old. The reference policy remains unchanged across batches. So pi old is a temporary snapshot used to update from the current batch. Pi reference is a fixed policy used to measure departure from the supervised model. Put all the pieces together for one batch. The current actor samples responses. Store the sampled tokens, their prefixes, and their log probabilities under both the actor and the fixed reference. The collection time actor becomes pi old for this batch. The reward model scores each completed response once. At every sampled token, form the reference term from the stored pi old and reference log probabilities. Add the response score only at the final valid token. These are the shaped rewards. The critic predicts the shaped return from each prefix. GAE combines those predictions with the shaped rewards to produce one advantage for every sampled token and one return target for every critic prediction. Keep the batch and pi old fixed during optimization. Recompute each sampled token's probability under the live actor. Form pi theta divided by pi old and update the actor with the Clipped PPO Objective. Train the critic toward its return targets. After the chosen update passes, discard the batch. The updated actor collects the next batch and becomes the new pi old. Only the actor and critic parameters change. The reward model and reference policy remain fixed. Now compare two measurements as training continues. The reward model score is used to train the actor. Held out human preference is measured using comparisons that do not enter training. At first, both measurements may rise. But with stronger optimization, the reward model score can continue rising even after held out human preference begins to fall. In some RLHF experiments, part of the increase in reward was also associated with answers becoming longer without a corresponding increase in human preference. PPO clipping limits the incentive for large favorable changes within the current batch. The reference penalty discourages the actor from moving too far from the supervised model. Neither mechanism tests whether the reward model still agrees with independent human judgments. A higher reward model score, therefore, does not by itself show that answer quality improved. That requires independent held-out evaluation. So what happens after 1.2? Add it at the final token and add the reference term at every sampled token. Together, these form the shaped rewards. At each prefix, the critic predicts the shaped return still to come. GAE compares those predictions with what followed and produces one advantage for each sampled token. A positive advantage pushes that token's probability up at that prefix. A negative advantage pushes it down. Its magnitude controls how strongly that sample contributes to the update. PPO compares the current probability with the stored old probability. Once a favorable change crosses the clipping threshold, this batch provides no further incentive to increase it. Then discard the batch and repeat with fresh samples. Across batches, reward favors higher scoring responses, while the reference terms resist excessive departure from the supervised model. That is how one final score becomes constrained updates to individual token probabilities. The score remains a learned proxy, so independent evaluation is still necessary.